Hello and welcome. I'm Gareth. And I'm Liam. And we're here today to record a short demonstration showing our NDT robotics and scanning solutions.
So we're going to show two key applications for large surface structure inspection. The first being external, so non-intrusive inspection, and the second being internal, so remote internal inspection. Let's have a look.
So this is our fully remote solution for NII. This is the RMS scanner, and we have different modalities for the RMS, which I'll work through as the demonstration continues. Set up here today is the RMS 600 on a flat wall plate, and we're starting off with a single crystal demonstration. So as I said, the system is fully remote. I'm actually set up on a laptop today, and I'm connected via TeamViewer to the instrument that you can't see in shot. But it just goes to show that the solution provides a fully remote control option, where maybe a level 1 technician could be in the field and a level 3 technician supporting from an office with setup, acquisition and analysis. Also could be used for auditing purposes as well. Of course, you can deploy it directly from the instrument itself, and with the Edify phased array instruments. All the motor control for the scanning solution is integrated. So if I start with the RMS itself, it's a magnetic crawler. It has a 240 kg pull-off force. This one, as I've said, is the RMS 600. There is a smaller version, the RMS 300, and a mid-range system, the RMS 450, which is predominantly for pipe work. The system itself has toolless quick release options. So for the single crystal that we've got set up right now, that can be quickly swapped out for phased array corrosion mapping and phased array top to weld inspection. So on the system itself, I'm just going to set up for a quick scan, moving in a standard raster formation. So it'll traverse across the scanning arm and then step forward at a predetermined step. The system can record data down to 0.5 millimeter resolution steps, but for the purpose of this test, then I'll just step forwards in a 5 millimeter step, and we'll collect data 2 millimeters across the bridge, so giving you an effective resolution of 2x5. On the integrated software itself, pause options and return to the 0 position on the scanning head itself, and we'll just start off now. So as I said, this is moving forward in 5 millimeter increments, and it's collecting data every 2 millimeters across the scanning arm. So I'll just pause the scanner there because it is quite loud, and I'll demonstrate to you how this can be detached and then fixed up with the phased array option. The advantages of the single crystal option is that it's a fully gimbaled arrangement, and therefore on maybe ship hulls or large storage tanks, you can get plate undulations. So it'll conform nicely to the surface, whilst keeping your data acquisition good. Also, an advantage of the single crystal application is that it can work up to temperatures of 220 centigrade with the increased length water bubbler, and that can be run with a standard water supply. So the RMS control box can work with either the phased array instrument, or there is an option to have an integrated UT board for the single crystal offering, where we look at integrating the UT board within the control unit itself. That then is run through a laptop, and of course when we deploy it with a phased array instrument, as I've mentioned, the motor control is all integrated along with the data acquisition on board. So now I'll demonstrate moving from the single crystal application over to the phased array corrosion mapping application. As I mentioned, there's a quick release interface plate on the bridge itself, so they can be very quickly interchanged. So I'll just disconnect the probe and the water and your single crystal bracket comes off. Just position the phased array mount onto the scanning head itself. And then this is our R-scan array. So the R-scan array has a water box and a 7.5 meg 64 element phased array probe as standard. The system is designed so that it's completely detachable, but then also it can be mounted for automated and remote scanning. So just position that. It's completely toolless, as you can see. So we got spring plungers which clamp the buggy into position, and now you're ready for phased array automated corrosion mapping. So now we're set up for a phased array corrosion mapping scan, and we're using the entry-level Mantis for this data acquisition. As you can see on the screen here, I've got my scanning control, and I've got a C scan, an A scan, and an E scan. Just a quick overview: the A scan is your ultrasonic pulse. Your C scan is going to provide the corrosion map with a color representation for every thickness. And your E scan is showing you the width of the volumetric beam. So I've set all the parameters. I'm just going to start data acquisition and then tell the scanner to start moving. So we're actually collecting at 1 millimeter resolution, so 1 by 1 millimeter resolution as we move up the wall plate. This scan is 400 millimeters long by 600 millimeters wide, and that'll give you approximately 240,000 individual thickness measurements that you can see that are displayed in the C scan presentation. So once we've collected the data set, we'll just select Save and Analyze, and I'll run through some of the analysis tools that are available in the Capture software. So on the C scan, as I mentioned, we've got a color representation for each thickness. So we can quite clearly see that we've got 3 indications on the screen. And if we move the crosshair to one of those indications, we've got a cross-sectional view of that corrosion pit on the wall plate itself. So there's digital readouts along the top. This jog menu can be removed, or it can just be scrolled along the screen. And at the top, as I mentioned, we've got plenty of options here to show the thickness measurement, the position of the defect within the grid, but also the remaining wall loss percentage as well. Just a note on some of the latest features of Capture. We can go into the indication table, and we can actually auto size. You can very quickly identify the minimum thickness on the defect itself. And on the Mantis, we can even take a screenshot and link it to that indication. So you can build up your report as you progress through each of the file size, each of the files that you've collected. So other things to note as well in terms of the analysis. There's a nice feature if we just press the C in the bottom corner. Sorry, I'm just trying to not block the screen there as I do that. And we go into the palette menu. So there's multiple palettes you can choose from, and you can change your the color representation or the amount of colors that are divided over the width of the gate. And once we've done that, we've got this really nice slider bar on the right hand side. So we can very, very quickly identify damage just by scrolling up through those colors. So you can see here that we've identified that there's 3 major defects in this plate, and we've already boxed off one of them and labeled it indication 1. A couple of other features available on Capture. we've got the floating gates. So if there's any low amplitude responses, then you get in post processing. You can go into the gate menu, and you're able to set a floating gate threshold, and you can see that it appears here on the A scan, and it will actually still capture the low amplitude indications for sizing. Also, all the gates can be moved in the post processing mode. So we can see we can just click and drag on the vertical cursors. You can also select the value and use the toggle on the right hand side. And once you've set your gates for the reprocessing, you just hit the OK button, and then it gives you the confirmation of whether you want to reprocess that scan. As mentioned, once you've collected all the indications, you can build these into an inspection table, and you can add them to a report. So we'll take another screenshot for example, add it to the inspection report, and it very quickly compiles into a report on the system, and it's recording your inspection context, specimen, transducers, and they're all selectable items. We've also got the inspection data and the screenshots which we captured for each indication. So it can be a real time saver when performing the inspection itself, so that you're able to easily provide a report to the end user in a very quick way. So as you've seen, the RMS automated system attaches with the R-scan array for phased array, and then also got the single crystal mount as well for the high temperature applications. The weld inspection on the 300 head, which is more compact. But where we move to other applications for piping or for manual deployment, of course the R-scan array can be used 4-inch and above. The RMS itself, the automated solution, is 6-inch and above, and also pairing with the R-scan array, and a complement to the R-scan array is our Link scanner. So our Links family is a combination of weld inspection, corrosion mapping for ferrous and non-ferrous items, for longitudinal and circumferential inspection. All the information is available on the website. But just a note that the water box and the probe in the R-scan array can be transitioned into the Links, so that there's a very good complementary system for the R-scan array for pipe work, especially when there's sort of low profile requirements, and also where you need full adaptability and reconfigurability for full NII scans. So we've covered the NII applications and what we get from the automated and the manual scanning solutions. Now we're going over to Liam so that we can see the RII, or the remote internal inspection side.
So as we've seen, Gareth has taken us through the NII, or non-intrusive inspection solutions, from the outside of a vessel looking in. But what do we do if we have a vessel that we can't access the outside? It could be there's loads of stuff around the outside. It could be that the vessel is buried, for example. Now, in these circumstances, we have our remote access, our remote internal inspection robots. So on the table in front of me here, I have our MAG 310, and this is actually our MAG 310 enabled. So effectively, this started life as a remote visual inspection robotic solution. We have a high definition tilting camera on the top here with a high magnification optical zoom. We have 2 tracks that are designed to give traction whilst crawling in different environments. And on the belly of the robot, you can see that we have these rare earth magnets. So these magnets keep the vehicle in contact with the side of a vessel. If you imagine the inside of a vessel, whether it's a a forecourt fuel storage vessel, so like 2 meters, 3 meters in diameter, all the way up to these really large in-service vessels, for example. The magnet never comes into contact with the surface, and that's a very important consideration. We have these rubber tracks. The rubber tracks are the only things that ever touch that vessel, and the real benefit to that is you've got no chance of damaging, or you mitigate quite heavily against the chance of damaging any of the coatings or liners that may be in place on some of these tanks or surfaces that we're crawling over. As you can see, we've got a number of different lights that are built into the actual camera itself. I'm not going to turn these on because it will interfere with this camera. And we've got some offset lighting as well, which is really important because as much as we use this camera for navigation inside a vessel to find where we are, we also use this to take really high quality images to try and understand what's happening inside there. Again, the reason we want to have a robot inside a vessel is because it's either undesirable, unsafe, or impossible to send a human inside this particular area or environment. So the ability to be able to see as much as possible and as best we can is really, really important. Now, on top of the visual inspection element, I mentioned before that Edify manufactures lots and lots of different sensors for NDT or non-destructive testing. Everything from ultrasonics to phased array ultrasonics, all the way through to ACFM, alternating current field measurement, and eddy current array, pulsed eddy current, for example, just to name a few. Now, one of the things that we really pride ourselves on within the NDT Robotics and Scanners Centre of Excellence is the simplicity of how the solutions that we have work. And as Gareth showed you earlier, we have the tool-free NDT brackets, which can be modular and adapted on the front of the RMS scanners that we showed you in the corner. Here we have a very similar principle which marries across. So for example, we have an NDT bracket here. This one is designed for single crystal UT, so conventional ultrasonics. It is very much a case of a simple bracket that clips in place, and again you've got a captive thumb screw which locks that into position. Now the robot itself can drive forwards and backwards, and we do that using a joystick, a very simple Xbox style joystick. You can move forwards or backwards. I'm doing this very, very slowly on top of this small table. And you've got the ability to raise or lower the actuator depending on the environment and how much pressure is going to be needed for that particular probe. Other examples of probe holders, just that we have in front of us here. So I've just got the UT and phased array probes today. We have a dry couple probe. So this is important. Again, a dry couple probe mount this is. The dry coupled probe has a rubber wheel that's had the same velocity as water, which means that you don't have to introduce lots of couplant into an area. Certain places we might not be able to introduce couplant, for example, and it's one less thing that you need to be able to consider. So something to consider when we're looking at robotic solutions for application of NDT in these types of environments where they're required is that the main reason that we're using a robot is because we don't want a human to access a specific area, or a human can't access that area, either because it's undesirable, it's unsafe, or physically we cannot get there. Good examples of this include operating subsea or submerged. So this particular robot can operate up to 60 meters submerged. The tether itself is up to 100 meters on this particular robot. And if I spin this around here, that's a horrible noise, I apologize. The tether that we have attached to the back of the robot, this is terminated here on the robot end, or the vehicle end, and this provides us with our communication and our control, so things like actuators, cameras, etc. And it also provides our mechanical connection. So should the robot need to be recovered, the tether is designed to take the weight of the robot within the environment that is being used. Coming back to the type of environment that we're operating in, of course we're relying on our visual inspection aids on the front of the system to navigate around and to place our probes. We've of course got a encoder built into the system which provides us the ability to capture like live B scans and encoded data. At the same time, you may have seen this flickering around here, we have these laser lines that project two laser lines that are defined width apart. This gives us the ability to track a weld or an avenue or an area that we would like to scan from an NDT perspective. So data acquisition on the Mag 310 enabled would be carried out from a UT perspective at least using the same instrument that Gareth showed earlier in exactly the same way. It would even have the same water pump attached. The bracketry is slightly different to match this particular robot versus the RMS that you can see in the bottom of the shot. But the connections and the instrumentation, the software, etc. that drives the NDT element is exactly the same. Now the robot, very, very simply, can be moved around the wall, and again in this case it's a carbon steel wall, using the joystick that we mentioned earlier. Again, you can rotate on the spot, you can go forwards, you can go backwards, and of course you have the ability to move over some of the more complex geometry such as welds and slightly different shaped areas. Now you can see, very faintly because of the light we have in this room, the laser lines that are projected on the weld plate that we have here. This is really helpful for aligning the robot when we're looking to carry out some form of non-destructive testing inspection alongside the visual inspection. And of course you've got this fully manipulable camera that you can rotate and move around. At the same time, you've got a number of different lighting options, including the internal lights and offset lighting, to be able to carry out some additional brightness if required. So when operating inside a vessel, you'll be using the visual inspection camera on the front to provide your line of sight and your first person view for manipulating and moving the robot around inside a vessel. When operating inside a vessel, we also suggest that correct tethering is considered. So as much as we suggested earlier, and we explained the blue tether attached to the back of the robot provides that mechanical connection, to be as safe as possible, if we're operating from extended heights or we're operating with operators below us, then of course there are a number of tethering points available on the robot itself.
So that's a wrap from us. We really do hope that you've enjoyed our short demonstration video covering some of our solutions for internal and external inspection.
Of course, this was just a very short snapshot. We've got lots of other solutions available, both robotic scanners and manned. And if you would like some more information, please don't hesitate to reach out directly. Our email addresses are on the screen below, and visit our website.